is time constants. We'll also say time constants and methods. So the first thing I'll note is for the time constant, when we say dA by dt equals k prime times a, so this is my, I'm going to do this first order. So if we're just saying first order reaction, right, we know that tau, the lifetime, was 1 over k for first order. Okay. I could also say 2 lifetimes would technically be 2 over k. 3 lifetimes would be 3 over k. So what about now under pseudo-first order conditions? When I say negative dA equals k prime times a. So when I'm using a k prime there, I recognize that's the pseudo-first order rate constant. So k prime is k times the B initial concentration. Okay? So now I can still use this notion of a lifetime under pseudo-first order conditions. Okay? But now instead of it being just 1 over k, it's going to be 1 over the second order k times the initial B concentration for the lifetime. Okay? And so we know that then 2 lifetimes will just be 2 over k times B initial, and so forth. Okay? So now how do we do these experiments? How do we do these exposure experiments? So I'm just going to do this very briefly. Okay, I could spend like a whole lecture on this, but essentially the way that you do one of these exposure experiments, the easiest thing to do is to hold time constant. Okay, so I'm going to say how we do exposure. I just got to erase it. How we do exposure experiments. First thing, hold time constant. So if you're holding time constant, then how do you vary that x-axis? Well, what you can do is use a flow tube. And this can actually be done in the gas phase or liquid phase. I'm going to describe this for the gas phase. But there's a lot of really cool kinetic work coming out with doing these types of flow tube experiments in the liquid phase using perielastic pumps, right? Pumping the reactants as a liquid phase through a constant cell. Okay, so in this flow cell, what ends up happening, I'll draw this like there's these little, places where the reactants can come in and then exit out, okay? So your time, because the flow cell is always the same dimension, if you're using the same flow rates, the time is always constant, okay? So now what you do is you pump in your reactant A, right, at some initial concentration, okay? And then what's going to come out of the flow tube is A at any time t. And really we recognize because the time is constant, the concentration of A won't change unless we change the concentration of B, okay? And furthermore, if we recognize that, in this experiment here, this was done through with the OH radical. OH radical is completely unstable. So what we actually did was in our flow tube, we surrounded this flow tube with a bank of UV lamps, and then we put in a precursor to OH radical. And when the OH radical entered this flow tube that was surrounded by UV lamps, then the OH radical is generated at a constant concentration, but only in the flow tube. And you change the X scale by jacking up the OH precursor for each experiment. Okay, so in other words, I will say we introduced some other reactant, C, okay? And typically, so I'll draw like here, like a little lamp something like that, right? Okay, we'll say this is like a UV lamp. And what's really cool about this, everything else in the experiment is completely blocked off from light. So we literally wrapped all the tubes and everything else in black cloth. And the only thing we kept exposed to light was the constant volume flow tube, right? So that we know that the time is always constant. And so now we impose some reaction that says like C under UV light makes our reactant B that we're interested in, right? We'll go back to this. You know, the reaction we're really interested in is A plus B goes to products, and we want to impose that B at any time is just constant, okay? So now what we do in an experiment, we flow in this C, but we know C under the UV lamp is really converted into the reactant that we want, okay? And then so how do we know how much B we created? Well, in a separate device, we monitor the remaining C that's left over. So now I know I said previously, well, the whole goal of this is to not have to monitor two reactants at once. Sometimes you have to do it. And the reason why we have to do it is because the OH radical is so reactive, we can't measure it. You can't measure the OH radical. It's too reactive. So then what we do instead is, well, we say that we put in a certain amount of C that won't be consumed. We know what the rate constant, we know what this rate constant is. You know, that's known. So we monitor simultaneously A and C. We often call this species C a tracer or even a precursor. So we can monitor that. So it's typically something stable that we can monitor. Okay. Then the way that we create each one of these data points. So all that I'm describing in one static experiment, all that does is generate like one data point. So then how do we get the time series of data points? Well, in each successive experiment, we just keep increasing the concentration of C, the precursor. We keep the same concentration of A initially, right? And so now in each experiment, we let this run through the flow tube. And by the way, in our experiments, this flow tube, it only took like a minute, you know what I mean, to get through. So it's under this steady state. So if we have a device that can measure concentration in real time, which I won't get into that. It was a really fancy mass spectrometer where we could measure, we didn't have to do any chromatography at all. We could measure concentration in real time. So then now your time is always constant. You're not doing a stopwatch, which is cool. Your instrument is just telling you, you know, any one of these data points. And now when you're ready to move on to the next data point, you increase the precursor. That generates more of B, the reactive species you're interested in, okay? And then your experiment shows you more of A is consumed, and then you keep doing it. You keep increasing the precursor C until you've reacted it all away, right? Because eventually, no A will make it out of the flow tube. You will have reacted it all away, which you can see down there. And very conveniently, you can now fit the data in this exposure space. That's what we call it, the exposure space instead of time space. And you recover your second order rate constant. So it's a really cool experimental method. It's not talked about at all in the book, but it's how we actually do kinetics in the real world.